We're live.
Okay, hi everyone. So this is another Wolfram Institute community forum. So the purpose of, well, actually, this particular kind of stream has a number of purposes, but really the key one for you all is we like to set aside time to engage with you all, to answer questions that you might have, to clarify points that we've made either on live streams or in something that we've written or on social media, and just overall to to dedicate some of our time to maintaining a kind of consistent discussion and conversation with you all. Now, while folks trickle in, we might just filibuster a little bit by discussing what we've been doing over the past week and maybe just chatting about some ideas that we ourselves are interested in, which could provoke some questions among the audience as well. So, I mean, I feel like I've spoken quite a bit during the past two fora. So, Nick, Carlos, Wukash, why don't you go ahead and tell some of the viewers, especially for those who haven't seen other streams, what we've all been doing lately.
Should I start? Yep.
Yeah, I think Carlos started last time, so I'm gonna keep track of this and
Okay.
rotate.
Well, recently I've just been mostly reading papers, like Sorkin papers, Raphael Sorkin, Fair Docker, about causal sets and like quantum measure theory. So I'm trying to understand how to connect these kind of ideas to a multi-way paradigm, because I think this idea of projections, observer projections on the causal graph, if you take a dual of it and take projections not on an observer chain but on observer anti-chain, and just basically make an observer like this anti-chain observer or branchially extended observer,
Yeah.
you may say, right? If you project events on this kind of observer, you can treat events there basically like uh, elemental events in probability theory, right?
Yeah.
It's like what happens and what not. It's like what outcomes are possible and what outcomes are not possible, right? And then and it's pretty clear how you can define classical probability with just sets of events, but how you can extend it to actual quantum probability is not so clear to me right now. So I'm just reading up on this quantum measure theory and how you can basically define quantum measure theory. So this kind of quantities as functional, just do it with events on
Well,
anti-chain.
so I mean, so one thing there is we have these world line models of observers, which on the one hand are consistent with what you'll find in, some textbook on relativity. On
Yeah.
the other hand, we're not particles, and so and I mean, that's just one thing, which is I keep making this point, but it's like the observer when you model an observer as a world line, it's like you're kind of modeling the observer positionally. Um, Whereas you need to also model the observer computationally. The observer doesn't just have some particular position and world line and reference frame, but also has some computational budget. The observer has some
Yeah.
kind of spatial
It's
extent,
just
et cetera, et cetera.
chain is just a minimal observer with
Yeah,
minimal
chains
computational
chains
budget.
the minimal and right, and so it's good because the chain is very much like the world line model that you find in your special and general relativity textbooks. But the question is how to kind of scale that up. Well, but one question, which is this is slightly different, is if we have a an observer chain, basically if we have some path in our causal graph corresponding to some world line, if you now take anti-chains,
Mhm.
if it has the right topological structure, can we model world sheets by taking not just one particular path in the causal graph, but because we also have these anti-chains filling in kind of two machine and machine-like fashion, actually getting larger world volumes as opposed to just the world lines themselves.
Now the thing is that the anti-chain, as I see it, is when you take a observer anti-chain and like opposite to observer chain, is you mod out the space completely. So the whole anti-chain observer is you treat it as the single location in space. So you have an
Hmm.
observer in one position of space, but it extended branchially.
Yes.
It's not actually like a worldsheet analogy. It's analogy that the observer is in superposition. It's like in multiple worlds, in the many world interpretation, right? All the possible observers in a particular location of space, because you basically assign a location of space because we associate this minimal observer chain with a particular atom of space. So you associate it to one position. So atom of space, minimal observer, and if you just focus on that particular atom or location, what how it manifests like in all branches in one particular computational step, right? So it's not really so it's this observer is not really extended spatially. This observer extended branchially. So kind of different idea. So yeah.
How would you account for I mean, the part of the world sheet idea is that there's, kind of quantum fuzziness.
Yeah.
Um,
So you can extend observers in many dimensions. You can extend them spatially by just bundling chains together, right?
yeah,
And presumably that also increases computational capability of an observer.
yes,
But also even a single chain, just by nature of a rule branching, can also extend an observer in a single spatial chain. Also can observe extended observer branchily. So just tracks an observer in multiple worlds. So
but
it can do different things
but
there.
what seems confusing to me is um, how are you differentiating between modeling the spatial extent of an observer and the branchial extent of the observer? So really different. One is how much space the observer occupies, in space time. The other one is how far the observer stretches across different, branching universes. They're pretty distinct from one another.
Well, you can differentiate it by just the nature of events, right? Because you know from the structure of the causal graphs which events, well, maybe not from the structure of the overall multi-way causal graph, but if you have
Mm,
a model, underlying computational model, for
hmm
example, with the hypergraph, you know which
hmm
atoms go where, and you know where the spatial, when the events are spatially disconnected or branch-wise disconnected. You can model out either the branch space or space completely, right? You just focus either on those events that branched because they truly in a single space occupy a single overlapping space and branch because of that, and
Yes.
or they just act on the different positions in space.
Okay. So the point there is you can model an observer's extent over different paths in the causal graph, but depending on whether or not there is space-like, depending on if there are space-like or branch-like connections or disconnections, the relationship between those paths could either be a a space-like relation or a branch-like relation, and they might look somewhat similar because the causal graph is such a parsimonious model, but really they correspond to very different things. Either, you occupy some space in a given universe, or you occupy some some interuniversal extent, and these are really quite different things.
Yeah, if you
Yeah.
like handle me a causal graph, a multi-way causal graph without any relations, there's no way of like separating which events, what are actually events constitute the space like disconnectedness or branch like, right? So this is like a property of a model.
Right. Okay. Well, we're going to probably discuss this in greater detail um, during the next stream. So, Carlos. Oh, well, we had a really great. I mean, everything's. I think I will say, the research is, I think, going quite well on all three fronts. Like everyone is working quite hard, and the balance between doing kind of fundamental, borderline scholarly research and actually finding computable examples, I think is actually going quite well. I mean, the kind of scholarly burden on each of you differs. Like Łukasz's is extreme. Carlos's um, is more moderate, but then Carlos has to learn more about Wolfram language at the moment, and Łukasz has to learn less. So there's kind of different levels of burden assigned to each of you, but all of these projects are moving forward. So that's exciting to see. So in Carlos's case, I mean, he just had many cool results to show yesterday. So I guess this is kind of a recap. Um,
Yeah, very
you
brief
could explain
recap.
briefly. Yeah.
Yeah, very briefly. As James just said, I've been learning more of a higher level functional programming part of Wolfram language. I've been, you know, getting my way with all this, finding my way around this functions of graphs and renders of different kind of like graph representations, things like that. And then, so yesterday I showed some of the early results in the sort of computational explorations that we're doing in this notion of emulation of two rewrite systems, Boolean algebra and combinators, SK combinators. So this is, I mean, one of the possibilities of how to study emulation. And what I'm excited about is that regardless of how well we do with combinators, I mean, there are some patterns that we saw yesterday, these isomorphisms between the multi-way graphs that you get after evaluations and things like that. I mean, the occurrences of patterns within the evaluation multi-way systems and things like that. This will have to explore to see if it takes us anywhere, but regardless of that, I think that having slowly developing towards a general functionality to do emulation of formal systems, I think is a very interesting line, because as we've discussed before with Nick and James in other streams, these formal systems really are, in a way, and this is the whole point of the Ruliad. I guess we can get into this later, but it's kind of arbitrary where you place yourself. I mean, maybe not arbitrary, but it's certainly a choice by the user, right? So if you place yourself on Boolean algebra, firmly on Boolean algebra as a read-write system or as a formal language, you are somehow making a natural choice for how human logic works and human language works and how we've communicated for thousands of years, and there's this predisposition to choose that particular computational system. Now, nobody sane would choose SK combinators to communicate in everyday life, obviously. And so it's this kind of divide that makes me quite excited to explore in the future the general notion of emulation and the general, because I mean, to be honest, that's what the true Ruliad is going to be, this quotient of the Ruliad under emulation relations, right? I mean, you're going to have
Yes. That's a good point. Yes.
That's that kind of approach, right? So anyway, so I'm excited about that. I think I will also be. I've been learning a little bit of the documentation on the functions that do axiomatic theory and things like that. You can do formal algebra. That's quite a bit of work done that was used in particular for the meta mathematics project and previous functions. So yes, it's quite exciting, making progress, learning the language. So hopefully the progress will even speed up.
Yes. Yeah. Carlos found some weird cases of isomorphisms that don't seem to, I mean, often they follow a certain pattern, but that pattern is also broken. And we also find examples where Boolean functions seem to be preserved under, in the intermediate steps where you have the SK combinator emulation evaluation of these Boolean expressions. Sometimes the Boolean, Boolean substance just completely disappears, and it's basically all just combinator plaque. Sometimes we see reappearance, and trying to determine whether or not that's coincidental or not will be important. And trying to understand when it is the case that Boolean functions are being preserved, if it is because of, especially in the multi-way case, if it's just a trivial matter of a delay in the application of the rewrite to a particular position, for instance. Trying to understand this more thoroughly over more case studies. I mean, if we do find cases where, in a kind of statistically robust sense, we see the retention of Boolean functionality, Boolean functions in the intermediate steps, where even some are being created or destroyed, or they disappear, or they reappear. And it's not just a matter of delayed, in a multi-way sense, application of particular rules in particular positions. So that'll be quite interesting. If it's the case that they just stick around because there is one path in the multi-way system where they last for a while, that's a different matter. But we have seen some, I think, for XOR and others, where you even have entire kind of grids that are multi-way, where you have something preserved for quite some time. Still, it could just be the case that it's the delayed application of a rule at a particular position. So this is really what we want to find out. Is there anything Boolean besides what you get in the beginning? Is it just that you have something Boolean in the beginning and then you lose it and then you kind of gain it at the end once again? Or is there anything non-trivial in those intermediate steps? So anyway, Carlos, maybe, I don't know, maybe it was the black background of the notebook, but it was a very, very, very nice notebook. It was very, very, very fun to see those examples. Okay, and Wukash, well, I will set the stage briefly for Wukash. Just, I don't know, I feel just to help the guy out. Not that he's not capable of doing it, but just because Langland is fucking difficult. So Wukash and I had a chat last night, and one thing that is becoming more obvious to me is that L functions, Dirichlet series, anything that you might use to study the behavior of the primes is really not too alien or dissimilar to the other kind of computational work that we do, where you have some behavior. That behavior is somewhat irreducible or difficult to grasp in advance, and you're trying to understand computationally what trying to understand the nature of that behavior computationally. So if you're looking at, say, the distribution of primes, some particular context, using something like an L function, the kind of analytic number theoretic approach where you're looking at things asymptotically, you're looking at things in terms of series and progressions, and you're studying qualities of primality. It's not quite rulology, but it is studying behavior that is irreducible, and you're doing it via this kind of, basically the kind of asymptotic instinct in analytic number theory is not unlike the kind of computational, run it and see what it does approach in like when you study Turing machines or cellular automata or something. And so I'm beginning to have this appreciation for art and L functions as something like a meta model of the primes for particular field extensions. I mean, what we often do when we try and model something by rulological means is you really try and strip the thing down to its bare essence so that you have some very simple seed, and then you take that simple seed and then you run it back out again after stripping it down to see kind of how it behaves. And with these art and L functions, I mean, you're going from field extensions to Galois groups, to generators of those Galois groups, to representations of those generators of those Galois groups, to characteristic polynomials that describe the matrix that represents the generator of your Galois group. So you're really stripping this thing down all the way to, in the abelian case of GL1, you're really stripping it down all the way to basically a complex number, and then you give it an analytic treatment. So that's, I mean, trying to find some way to couch this within language that's more familiar to me, I personally find it to be quite helpful. And also, I think it's going to be important for when we start to treat this kind of thing mathematically. So anyway, that's kind of my take on this. But Wukash might have more to say.
Yeah, recently I'm feeling like I'm starting to get a big picture. Like I looked into analytic number theory and all that stuff in previous week. And yeah, maybe let's not go down to the level of what is group and what is real. But
yeah, sure.
Yeah, let's say it's a background knowledge. So yeah. So basically, you have your field and you have your field extension, and in your field you have integers. and there are primes within these integers, or think of ideals of the ring rather than just elements, but whatever. You have your prime ideals, and they are distributed somehow. And now you extend your field, and you have more of your integers, so part of your primes may cease to be primes. Like if you have Gaussian integers, then 5, for example, is no longer a prime because it factors into 1, 2 plus I, 2, 1 plus 2i, and 1 minus 2i. Yeah, and okay, and now you generate Euler product from your primes, and you can generate many different functions with this Euler product. You can ask different questions, and it really depends what you want. You can ask about squareful primes or whatever. Squareful numbers, not primes. And basically, there's this interplay between Euler products and Dirichlet series. And how one translates into the other depends on the distribution of primes in your field, in your structure. Yep. And now we have this.
Oh, yeah, go ahead.
Now we have these field extensions. So you had your primes, and now you extend your field with some elements, like square root of -1, and then some of the primes are no longer primes.
Mm-hmm.
And so the part of the information about the new distribution of your primes is sort of encoded in the Galois group of your field extension and in permuting the roots and everything.
Yep.
Yep, and I think the Langlands program is really about that. From one side, you have distribution of your primes. How, like, you have the fact how it changed, the distribution of your primes, encoded in the Galois group of your field extension. And on the other hand, you have it encoded in this Dirichlet series and all sorts of stuff. And you try to connect these two islands.
You try to connect those islands, but also you try and connect these different L functions. And that's the kind of higher level. One thing that I think, just to make a conjecture, one thing that we might end up doing is, I'm always asking, are things multi? Are they not multi? And doing it like these progressions, Euler products, for instance, L functions, they I could be wrong. If someone wants to make the other side of the argument, I'll be really thrilled. But they strike me as not particularly multi-way. They strike me as you have some particular series, you're taking some particular product, and that's just a kind of a normal calculation. However, the whole point in functoriality is that you have, on the one hand, you can make changes on, say, the Galois extension side, and on the automorphic side, which we'll see in due course, you can do this thing called base change, and there'll be some functorial correspondence between these different L functions. So I do wonder if, even if L functions themselves are, they are kind of releological in the sense that you're kind of grinding down field extensions to really kind of basic generators, like Frobenius, like representations of Frobenius elements. And then you're running their analytic behavior, which is not unlike just computing a cellular automata and seeing what it does. But even if those are single way, that functoriality is going to be some multi-way picture where you're considering different L functions according to, on the automorphic side, different base changes, and on the number theoretic side, changes with respect to, say, your field extensions, for instance. So that's, I mean, I'd like to make, I don't know, kind of provocations help me at least, like, determine with time if I have any grasp of what's happening, but that would be my if I had to try and relate like Langland's functoriality to say a multi-way system for different cellular automata, where you have many, you have many different threads, really logical threads, and then you're trying to understand the relationship. And that would kind of be my guess at the moment. That functoriality it becomes a kind of multi-way picture of analytic number theory. Okay, yeah, that's a clean way of saying it. So we'll see. Well, so I'm not sure if there are questions yet in the chat, but why don't we open this up and just riff about some stuff. This is always a good venue for that. Boy, Wukash seems okay, but Nick and Carlos, you guys seem tired, man. You know we have another stream after this, right?
I'm fine.
No.
And it's with a stream with a guy who's twice your age and has 10 times your energy. So you gotta get ready.
Yeah.
Well, Carlos, look, Carlos, I'm gonna scapegoat Carlos. Carlos put some profound topics in the description of this stream, and so it would be bad if we didn't discuss some of these. But Carlos, you're to blame for putting, consciousness and observers and rheology in the description. So
I mean, I'm just I'm just collecting what the
should,
community has voiced in the last few days. I mean, in general.
No, I know. I'm just I'm mostly kidding, but
yeah, but for sure, let's go ahead.
Yeah, well, Carlos is kind of the community master in some sense. I have seen questions about, I mean, I've been answering questions about the Ruliad. I've been answering some questions about observers and consciousness, but I mean, Carlos, was there something in particular either that hasn't been answered or that has been answered but you thought was quite interesting that you want to bring up?
I mean, actually, it goes back to week 1, but there's been this, I think, quite a lot of interest around the question of whether the Ruliad. So this idea of if there is computation going on, where is the computer, right? So
Yes.
So this entire topic, I think that, I mean, it's been answered. You've given answers, and people have discussed it and everything. But I think it's something that it is quite fundamental to whatever we want to think about in terms of our last conversation about the Ruliad. Certainly left me with a clearer picture because, we had this example of, one particular system that could be embedded in a larger system, and that's sort of the Ruliad of a particular system makes sense, and you think of the disjoint union of all the Ruliads of all systems, and okay, that makes sense. But I think that both in terms of what is a rule in itself, what is the Ruliad made of,
Yes.
and
Yes.
this angle of if there is computation, where is the computer? I mean, I'm characterizing, right? I'm sort of
Yeah.
making a caricature of the argument, but I think those are interesting questions to circulate among the four of us because I would like to know what your thoughts are. But you, I mean, the four of us, and I think people would appreciate because there's constant. I mean, it comes up constantly. I mean, even in just
It comes up constantly. Yeah.
brackets.
Well, I explained this just a little bit, but I'll give like the 1-minute version. This will appear in this End Machine Theory bulletin, which has just been very slow for some internal like reasons, but it should be published really soon. It's done. It's just like getting ground through the editorial process, etc. But I really tried to disaggregate and dissect the definition we have of the Ruliad. So the Ruliad is this synthetic space that's composed from the computations of all rules from all initial conditions run until, I mean, I think the informal definition is like it's run for all time, but it's run really to like, we're not dealing in hypercomputation or anything. So it's like, it's run up to, if not, it's not higher than that. There are bounds on the Ruliad. But okay, so that's the description of the Ruliad. The Ruliad is formed from the computations of these rules. But what about the rules, and what about computation itself? And so, I mean, my own take, which I kind of described briefly before, and I'll describe even more briefly now, is there's no reason why rules themselves should be a part of the Ruliad. Rules are just these things that are possible, and then they become manifest in the Ruliad by way of computation. And computation is making animate these rules in the Ruliad. And so, I mean, the kind of mathematical or pre-mathematical definition of a machine that I have going right now is a machine is basically, this kind of functor from these rules, which are these, groupoids in some pre-Ruliad that that establish relations between these different states, but they're atemporal and they're not known. And when you actually compute some rule from an initial condition, then you start to actually see the relations between these states, and you have to use higher end machines to see all the different relations. So in some sense, a machine is something that's also outside of the Ruliad, but is um, is kind of laying the bricks piece by piece that compose the space within the Ruliad. And that's basically my take. If the Ruliad is this kind of structure that's pieced together by computations, then it's like the kind of instructions for those are inherent to the definition, and also this like laying of these kind of bricks, whether they're particular edges between states or they're higher simplices in the end machine case. They're just these kind of relations between states that are being kind of laid one at a time. And so, when people ask where is the computer that's making things happen, I mean, I know that Stephen, for instance, I don't think Stephen likes this question because, and I used to not like the question either because, the point I used to make was, well, you can just think of nature itself as this kind of computational process, but then you still have to answer this question, which actually Manuel Blum, for people who know Manuel Blum, actually asked a really nice version of this, which is like, what puts the fire in a computation? Like, why do computations even happen? And of course, that has to do with things like pattern matching, etc. But you could even just ask, like, you have rules. Rules are possible, but then why do things become animate? If the world can be described in terms of computations, why is there a world as opposed to just something that is possible? And what's the difference between just some possible world and a world actually being phenomenologically experienced as the rules that govern its behavior are actually being played out? So these are just like really, really deep questions. Absolutely. Yeah.
How do you think about it, Nick or Łukasz?
Boy, I kind of think, yeah, it's quite a silly question, because when you talk about computational universe, right? Computational universe, mathematical universe, clockwork universe, like, right? It's the same thing. You don't have to like equate it to an actual physical world. You don't actually think that some clockwork ticking is actually what actually happens in the world, ontologically, like, right? There doesn't have to be a fuel that fires it, fuels it, or like ignites it or whatever, right? It's just a useful language to talk about the universe, but it doesn't have to be something actually in the universe. Or actually, otherwise it just never. It's not scientific questions even. You will never answer it. There's no possible way to answer it. Why even ask it?
Yeah, I'm with you, Nick. I have similar sentiment in terms of committing ontologically to whatever your model is saying. Because, I mean, the people take. I was actually in conversation with, you might know this guy, the person who runs the channel Theories for Everything. He interviewed Stephen a few months ago, and I know the guy. We're friends, and we were chatting. I was like, oh, all right, how's the job in the Wolfram Institute? And we were chatting about this model, and he said, of course, because of this model, I'm thinking in terms of discrete elements of space time and whatnot, and I was saying, well, I'm curious to see what my colleagues think, because I personally don't commit to either discrete or continuous, in the sense that, I mean, I've done most of my research in my life in continuous mathematics. Now I'm doing much more in discrete mathematics, and they both bear fruit equally. So I mean, I can't say, oh yeah, it has to be discrete. I mean, obviously it has to be discrete. I mean, this ontological commitment seems to me very artificial, and it's something that, you know, it's in the realm of belief, in the realm of aesthetics, in the realm of sort of some more speculative philosophy and things like that, that you want to, I mean, you want to discuss it. I mean, there are some valid points to be made about whether a fundamentally continuous or fundamentally discrete model is going to take you to this different lengths. I mean, this is a thing to debate, but to try to claim that nature really is that way or something like that is, as you say, I mean, it's an unscientific question. So why ask it, right? So,
Yeah, you would never prove that world is continuous, right?
yeah,
It's not even wrong.
yeah, it's not even wrong.
So
Exactly. Yeah.
yeah, so you might as well say it's discrete and continuous is just a limit of it.
Yep.
Yeah, so it's just
Yeah.
two useful frameworks to talk about, and that's it. Sometimes
Yep.
it's useful to describe it continuously, sometimes discrete. But
I
discrete
think,
is not even wrong,
yeah,
so continuous is you can't even prove it wrong, so it doesn't make sense to call everything continuous. So continuous is a useful model, but to call world continuous, it doesn't make sense to me. So
yeah. I
discrete
mean,
is much cooler.
in ter the main responsibility that I feel is there. This notion of the Ruled has attracted some interest, and I think that it's attracted interest in part because it's this kind of highly, it's in some sense it's this all-encompassing object, but in also some sense it provides people with some kind of foundational excitement. And I think people are interested in kind of fundamental questions of, you know, where do things come from, et cetera, et cetera. And, you know, these kind of questions often test the limits of science, or as many people will feel, they kind of lie kind of beyond the purview of science. And I mean, one thing that I want to do though as an exercise is try and understand, can I at least set up a kind of basic model, you know, with notation that's computational, that's functional for the Ruled, where I'm kind of taking apart these different pieces of the Ruled, you know, distinguishing rules from computation, from the spaces from computation, and whether or not ontologically you can say this is how the world works is, you know, is one question. But you can certainly, you know, constructively view the Ruled as this legitimate kind of computational limiting object. And then the question is, if you are actually going to piece that apart and not make any assumptions and kind of disentangle it and dissect it into its various parts, how would those parts kind of fit together? And then it's like, you know, it's up to people to decide, like, you know, is there a Ruled? Is there a pre-Ruled? You know, how does machinery really fit in? Do we want to just treat everything as possible, et cetera, et cetera? But I think trying to take the concept seriously and just trying to understand its implications, simply as a kind of thoroughgoing exercise. Like we have this interesting concept. What are the kind of implications, or what would make the description kind of fully robust? And yeah, because it's a very fundamental object. If you try and if you make ontological commitments that correspond to the descriptions, then they're like these highly, you know, they're like these highly fundamental ontological commitments that almost arise, you know, they almost become like theological commitments, definitely. And so, you know, you can, I mean, well, I won't object if people make ontological commitments. You gotta, you know, humans have done that for thousands of years, but you don't have to. And maybe you shouldn't. I don't know.
Lukash, any thoughts?
Well, like, I mean, we should make a clear distinction between scientific and philosophical discussion, especially on something like community forum. Because like for non-experts, like I mean, really non-experts, it may be difficult to distinguish when we just discuss something that that is scientific and we can check that in the near future, and what is pure speculation, and maybe they shouldn't listen to us like any more than any other guy, any other random guy. Like I don't have a background in philosophy, and I don't know if you you have, but we're not philosophers. I think like we can discuss it of course, but yeah, we can make
What is the
but it's really
prerequisite to be a philosopher?
it's really amusing that
Like,
Wukash,
I don't know.
who's like, I don't even hold on. I don't even know how old Wukash is. He's like 19 or something. He's studying the Langlands program, and then he's scared to dip his toe into the into the philosophy world. That's that's interesting. Wukash is basically fearless when it comes to studying PhD level math, but he's I've taken a long-standing interest in philosophy. Someone was asking me, I think it was Kartik, whom we know, was asking, can we write up some actual piece on how rheology, the Rhuliad, the physics project relates to philosophy? And to some extent, I've been saving that work for Hatem, because Hatem has kind of had the title of our kind of philosopher. But, there's actually, the world of philosophy, the canon, the literature, is just huge. And like my own interests, like in Kant, Quine, etc., even going out to maybe even people like Derrida. I mean, everyone can take their own particular interests in philosophy, and then there's just a lot to say about what we're doing and how it relates to philosophy. So I might write my own piece on like these are all the philosophical arguments. These are all the particular philosophers whom I find interesting, and whose ideas inform ways in which you can look at all of this. So I mean, Wukash makes a fine point, which is, yeah. So one methodological point is I don't really like it when people relegate undisciplined aspects of their thinking to the title of philosophy. It doesn't do service to philosophy at all. So philosophy is a serious thing. So when people say, "Oh, on a more philosophical remark," what they just mean is like, I'm gonna just say some random opinion, or I'm just gonna, say something that I can't back up. And it's like that's kind of, it does a disservice to philosophy. So I mean, yeah, these questions, once you get into really the kind of deep level of the Rhuliad, I mean, it's all philosophy, but it could be done in a serious way philosophically. And I think because that will be, that at least, not everyone will necessarily pay attention to it, but because that is something at least that I care about, which is like the kind of underlying philosophical foundations of things like the physics project, it should just be done. Like someone should actually do a real philosophical take. Like Stephen sometimes describes his work as like, oh yeah, this is partly philosophy, but it's not like he's not like he's really engaging with Heidegger and with with various people. It's just like here I'm going to kind of riff, and riffing. I mean, this is kind of what Nietzsche did with his kind of aphoristic approach to philosophy, where you're basically just riffing. But of course, Nietzsche also knew his philosophers too. And so I think doing real philosophical work on this will require dialogue with people who have philosophized in the past, and there are many people who have philosophized well in the past, with whom we could have some discussion, at least a textual one.
Yeah, I mean something that.
Does anyone else?
Yeah, go on.
Well, does anyone else here have an interest in philosophy? Has anyone studied philosophy informally, formally, semi-formally?
I mean, I was just going to say,
Just a little bit.
I mean, I don't really, I've not really ever been interested in scholarly philosophy, so in the academic philosophy, in what normally now today is referred to as philosophy, just plain philosophy. I am interested in obviously the etymological sense of philosophy, and how.
You mean the love of knowledge?
Yes.
Yeah. Yeah.
No, but I don't mean it just in terms of I'm a scientist. I like that stuff, but I mean it in the sense that I mean essentially my entire career has been based on going at the foundations, thinking hard about what things mean, looking at the world, and just trying to be as foundational, as fundamental as possible, and then going back and doing all your rigorous science, rigorous methods and whatnot. And the thing is, modern philosophy, or what people normally refer to as philosophy, which really should be called academic philosophy, leaves me very cold, to be honest, because I think science has offshooted off of philosophy in the last 400 years or so. Before they were kind of intertwined, no real difference between them. But the moment that we started doing mathematics and systematic science in this empirical way, and started with scientific method as a prototype and as a program more than any kind of dogma that some people try to associate, that started to actually demarcate itself away from philosophy. And I think a lot of good philosophy has been done ever since. There's been incredible advances in just pure linguistic thinking, but linguistic thinking is very limited, right? Like you can't do much with just language, and philosophers have essentially just been using linguistic thinking to go at everything over and over again, and again, to the point where they say it is part of our brand that questions are left unanswered. I've heard this for many philosophers, that the point of philosophy is to ask questions, not to answer them, which is kind of a slogan that you hear a lot. And this is okay, but I think many philosophers in the past would never say that. They would never say, oh yeah, our point, our goal in history is to just ask the questions and never answer them. Ask this to Leibniz, ask it to Newton, right? Come on. Clearly they were not going to say, yeah, we're just asking the questions. So I think that's what leaves me cold about modern philosophy, that is very specialized to be sort of self-justifying with systematic science going on at the same time. So yeah.
Sure. Yeah. I think where philosophy becomes very useful today, especially when you're doing, say, computational research, is, I would say if you have a new instinct or a new line of reasoning or a new hypothesis, or you're kind of inventing a new field, I would say you are doing some philosophical work in this kind of weird sense that, at least kind of culturally, when you're thinking and you're not thinking within an established tradition, people will often view it as being philosophy, in the sense that it's almost like philosophy in a kind of dystopian world. Philosophy is now this term that you use to describe, somewhat original, independent, risk-taking lines of thinking. But when you are actually doing things computationally, I think that the risk of just being way off is highly diminished, because it's like, if you have, I'll give you guys conjectures, functoriality will ultimately be, a multi-computational view of analytic number theory, or you will find when you take emulations by SK combinations of these Boolean, you're going to find combinations of machine CRUD and Boolean expressions. These are just guesses. I don't know, but sometimes they're right, sometimes they're wrong, sometimes they're misinformed, sometimes they're more correctly informed. But they're all just it's all just kind of intuition that, I like to think in intuitional terms, and I always feel kind of well backed by the fact that these things can always be made concrete and computational. So, this is something that Steve and I both agree on, is I think there should be a much greater push for kind of philosophical thinking, though not necessarily in the tradition of, not in the tradition of Spinoza or Hegel or what have you, but I do think things like philosophy of science, especially, I particularly like Quine quite a bit, but asking kind of more deep questions and really trying to develop intuition, and then backing up that intuition by doing work that's highly constructivist, where you're really accountable for everything that you're saying. I think that this is still highly preliminary, but I think it will become a very strong methodology as we continue to use it, where you have more license to think outside of traditional boundaries, but it's because you have tools and methods that are so sophisticated that you're very quickly able to make things concrete, even though they're highly new and decoupled from some particular line of a citation network.
Yeah, but the question you asked are basically scientific, somewhat scientific. You can compute the answer to them. You can check the answer. But what about questions like, what is the computation running on? What animates the rules?
Oh,
Like,
we don't have no, we don't have
yeah,
any access to it. I mean,
yeah, you would need
it's
Hyperrulette to compute the answer to that
yeah,
question.
it's completely numinal, right? In the Kantian sense.
Yeah,
Now,
these are, I think, like pure philosophical questions. Like,
now we have another stream that's scheduled for 1 minute ago. I did see Will Yam Yam and Spare Parts 2 did ask questions, and I feel bad that we did not answer them. Um,
I mean, we can move
well,
to the next. We can move to the next stream. Are we gonna wait for Steven to be on and then we go live, or are we just going live and waiting for him to
well,
join?
we don't know because it's a different Zoom room, so he could be waiting right now.
Okay,
We
let's
actually
go.
don't know.
Let's go then.
So yeah, we should go. Thanks everyone. Hey, if you want to continue watching, we're about to do another stream with Steven, who's for all intents and purposes a cool guy. And so we're going to discuss observer theory and yeah, this will be our first stream with him actually. So
Yeah.
stay tuned. We'll be right back after these messages. All right. Yeah. Okay, cool.
We are live.
All right, everyone. This is another Wolfram Institute live stream, and today we have a special guest, a man who really does not need much introduction, Stephen. So, Stephen, thanks for setting
Hello.
aside some time to meet with us. What we're going to do is we're going to continue a conversation that we began a few days ago, though with some review, both for the sake of our viewers and for the benefit of Stephen, so he's not completely lost. So, Nick has been really taking the lead on the physics project and revisiting some of the fundamental aspects of the physics project from computational foundations. So in particular, we have been reviewing chapter 8 from the physics book, particular section 8.3, in which a number of these physical quantities are provisionally, speculatively, provocatively defined in various computational ways with respect to the initial modeling framework that's introduced in the physics text. And as we began to think seriously about how, for arbitrary hypergraph rewriting and for some arbitrary candidate universe, we were going to extract these values, it became clear that even for things like, say, velocity, we were going to need to make inroads towards observer theory rather quickly. And so Nick has been doing some review and has some new computational concepts such as observer chains and even this thing called observer anti-chains, which we're going to discuss hopefully today. But essentially, Nick has a way to basically model observer world lines and begin to coordinatize events with respect to different observer reference frames. Now, this is a kind of highly rudimentary way in which observers are modeled, say in some textbook on relativity. And I think that modeling observers basically positionally via some kind of world line analogy is fine. But observers are not just positional, and they're not adequately just modeled via reference frames or foliations. Observers also have computational budgets. They also have things like spatial extents. And so this is also, these are higher desiderata of a greater theory of observers that in our models we really need to have. And so at the moment, we have what you would find in a physics textbook where you just have some particular chain, some particular world line, but obviously we're not Eames. We consist of many Eames. And so to get to, from this basic world line picture to something where you're modeling observers of various sophistication, this is a higher goal. We'll need this for things like SETI, METI, etc. So that's just a bit of an overview for people who haven't been watching the streams and also for Stephen. That's what we have been discussing, and that also describes what we're about to dive into. So Nick, please, why don't you kind of go ahead and give a summary of observer chains once again, just for people's benefit, and we can
show us some world lines.
Yeah.
Okay, that's a causal graph.
Yeah. So should I do a review or like
do a review? Stephen hasn't seen this.
Yeah. Sure. So the basic idea, right? If you take any causal graph, you model the observer as a time-wide curve, right?
Yep.
Or chain.
Yep.
Right. So basically, the picture, this is like a bundle of observers in this picture. For any causal graph, you can do it. You just find a path from a source to a sink, and this is your observer, right?
In what sense? Wait. There are observers who are inertial in some sense, and there are observers who are sort of zooming around at different. You're going to say.
Yeah.
First thing is there are many possible time-like curves that can be drawn through this causal graph, and
the inertial observer basically. You have to take at least two observers in order to say whether one of those is inertial. So this is where the projection of events on these chains comes into place. As soon as you take like two observers here, for example, in order to say, it's like I took this example, I took this like idea of observer chains and projections from this guy called Kevin Knut, right? He has all these ideas of his influence theory and these chains and how the space-time emerges from this, right? And his idea that he kind of have a basic idea of observer, not just arbitrary time-like chain like that, but also pairs of chains that in some way coordinatized nicely. The way that like if you just take one event and project it to the other observer and then project it back and back and back, you kind of get the same intervals all the time.
Well, Nick, you're actually going to show
observer.
that. You're going to show that concretely further down. So I
Well,
think the short.
In relativity, right? I mean, so you have a world line, and as I recall, there are these constructions like the shield ladder construction, where you have a crisscross, photons going back and forth between two parallel things.
Mirrors.
And and so you're trying to construct, for example, are you trying to construct two parallel world lines or just any two world lines?
So for now, I don't try to construct two parallel lines. I can find those if I want.
Okay.
Right?
Okay.
If I manage to find actual parallel things that project nicely to each other, I can call it inertial observers. If they're not, they're just not inertial, but it's just arbitrary observer.
Okay.
Right? And so next, it's like I have this. You can take the same idea and just make it computational, not just for arbitrary, like a causal graph, but you can actually find it like in any computational, like causal graph, like from the Wolfram model.
Right.
And the way I did it is you actually can label each of the events, but what EMs they take as an input and what EMs they produce, right? And in this case, actual EMs is not actually vertices in the hypergraph, but some index that you assign to a hyperedge. So it's a little bit different. So, right? And then you can just say
the carrier of causal information, this is one of the issues, is what is the carrier of causal information? Is it a hyperedge? Is it an atom of space? It's presumably a hyperedge, because that's the thing that's being concealed.
It is a hyperedge.
Yeah, that's what he's saying.
Yeah. So that's basically what this code is doing, is just basically some manipulation of the Wolfram model object and indexing those hyperedges so that I can label those events.
Right.
And then when I label it this way, I can actually just focus and track each particular index there or EM causally. Mm-hmm. And I just say that this is my observer. This is like different observer chains, depending on what particular EM I'm tracking.
Yeah, but it's still, it's like an EM level observer, which computationally is trivial, but it's the starting point. Yeah. Right.
But just so I understand, I mean, in standard special relativity, one is just dealing with world lines. And, even in general relativity, one's dealing with, point test particles and things like that. So I don't think, in standard relativistic kinds of things, I don't think one has gotten beyond kind of the point observer. We will no doubt have to get beyond the point observer.
Right. That's what I was saying in the intro. I mean, I've been highly distressed to see, it's like I've seen these things in like these relativity books where it's like you have some world line and then you zoom in on it and there's some picture of somebody, in a laboratory. And it's like, crying out loud, like we're not particles. I mean, it's position. It's a positional description of the observer, right? But it's not a computational one.
Right, but the problem is in relativity. The problem has been extended objects are hard to deal with in relativity.
Right.
And I don't know what for us. In relativity, you assume you know what an object is, like it's a pole and it's made of a solid object or something, and then you try and fit relativity into that. For us, we're coming at it from the other side. We don't yet know how to make objects out of things, and we have to have some, something. So there's no problem with the relativistic aspect of what we're doing. The problem is with the making objects aspect, which is sort of the thing that's assumed to be understood in the typical relativity textbook situation, where a lot of very silly things end up getting said because of this mismatch between what can be described relativistically and what is everyday experience for objects. Okay, in any case.
Yeah, I agree.
So basically, you can cross-grain. It's a problem of cross-graining of events, right? You can just treat like these three observers. You can cross-grain, you can foliate it, and just foliate each slice, just bundle all the events into one. And just call the new chain that's being produced by a bundle of those a new observer. And now it's a spatially extended one. And obviously more computationally capable, because now it not only a single track EM, but more than one.
But so, I mean, in general relativity, for example, if I remember correctly, there are, these pencils of rays and things like this, which are the same kind of idea of multiple world lines and looking at, and one knows things like, the effect of curvature is to take a bundle of world lines and change the shape of the cross section of that bundle and things like this. So this is so that's its version of such a thing. But yes, this is okay. I understand. This is a sensible thing to
Well,
do.
presumably you can extract all of this information from just projecting. Well, the idea is just you can extract every information of space-time, dimensionality, curvature by just projecting events. So order gives rise to all of those quantities. Nothing else. And presumably some foliation too. And just a quick look at what would that look in the multi-way case, briefly. It's just in the multi-way case, if you do the same kind of thing by tracking an IM, now you no longer have a single chain, but you can have this same IM in multiple branches. So now you have a branchily extended observer.
Yep.
Yeah, and we'll get back to this case, to the multi-way case later a little bit. But right now, I want to just show how you actually derive some of the special relativity quantities from just projecting those events.
Okay.
Right. So now the idea, now when you have a chain like this, you can kind of label each of the events around it with some pairs of numbers, or just a single number, depending on how you project it to the future or to the past. Right. So this event has a future projection on this observer, and this is like just a naive quantification on observer, and you can label each of these events. Sometimes the label is missing, but the idea is that you just have to label it somehow, right?
So this is from Knuth's text. You have a world line, time running upwards, and you're coordinatizing events that are outside of that world line relative to the world line, depending on the causal relations in the greater causal graph. This is the idea. Right?
Okay, question. I mean, this person's work, are they coming out of a causal set tradition or something completely different?
Yeah, well, he mentions causal sets quite frequently, but but this like projection idea, it's somehow parallel to it, or at least it's much simplistic. So that's why I like it in a way. You can derive it more explicitly by just doing.
So what you're saying is you start a future light cone and a past light cone. So you've got that like that 0.62, for example. The past light cone 6.2 intersects the world line at 6. And intersects the future light cone.
This is the future one. Yeah.
Oh, which way is time going?
I think because it's 1, 2, 3, it goes.
Okay, I'm totally confused by that. Okay, well,
I know. I would do it down as well. I know.
But okay, no problem. So fair enough. So what's happening then is, from any given event, you can construct its light cone, and its light cone will have its future light cone will have a unique intersection point with the time-light curve. Is that correct?
Well, it's not unique. There's probably going to be many. Like here, you have 6 and 7 both intersecting, but you have to find the lowest one, the first influence. Because Knuth calls it influence theory because you can think of it as this event actually influences an observer in this event. Like here, the actual interaction happening.
Well, I mean, you're saying that the other one is not transitively reduced, so to speak. The other one, you're first going through. I'm a little confused. So you start a future light cone from an event. You have a time-light curve, and there is. I don't understand. There's the exterior of the light cone. Doesn't it have a unique intersection point with a time-light curve?
Well, the exterior, yeah. If you think of it as an exterior, I think you call it like a cone as a whole bulk, just vertex out component. If you just take the vertex out component of this vertex, basically, and where it intersects it, you have to also find the lowest one. And well, you can say the same if you just take the intersection with the boundary.
But lowest as in it is the place that is the shortest graph distance from the source for the time-like curve. Is that correct?
Yeah. There's actually a resource function now that I submitted that called lowest. This doesn't. I think it's lowest. Oh yeah, I think it's. Why doesn't that? I already forgot how it's called. I think it's called lowest common ancestor.
Okay.
For a
Like
graph.
it's at what earliest time the event can influence the observer?
What's that?
You sure that's
What-
what it's
what-
called, Nick?
What is the earliest time the event can influence the observer?
Yes. Right. Earliest observer time that the
Earliest
event
observer time.
observer. Right, where the observer time is measured by essentially graph distance along the time-like curve that is representing this observer. So when there's an extended observer, it's a little less obvious because the observer's left tentacle could be affected before the right tentacle is affected, so to speak. And because if the observer is extended, right, there's a light travel time between the left tentacle and the right tentacle of the octopus, observer type thing. And so this definition, it's not obvious how this definition extends to an extended observer.
Well, yeah, for the extended one, well, we don't have to think of it because the point is that you use only the single chain in order to quantify all the events.
Okay, fine.
So it may be a boundary of your extended observer or something.
Okay.
Right. And so now here's a naive quantification of an observer. You can also quantify it with the foliation, of course, but it doesn't matter for some reason. You can, if you have a foliation of a causal graph, instead of just counting numbers naturally, you can also count it by depending on what your foliation slice is.
Well, so the point of a foliation is, given any time-like curve, the foliation says for all time-like curves, the foliation is a way of essentially coordinatizing all time-like curves, so that
simultaneously.
right, so that.
Yeah.
But in general, the coordination of the time-like curve that you've given here is just the counting numbers. You're just counting graph edges. But when there's a foliation doing this, there might be several graph edges in the time-like curve that were all in the same slice of the foliation. Is that correct?
Well, sure, but it can be, but the point is just that it's just changing the numbering scheme, nothing else.
Yeah, but some of the numbers could be identical. Like 5 and 6 could be in the same slice of the foliation.
No, they can't be because they're time-like connected. So by definition of foliation, 5 and 6 should be in different slices.
Okay, fine. But they might be they might be 3 slices away from each other. There's no guarantee.
Yeah, they can skip. There can be gaps basically in this scheme. And the single observer can have gaps.
Right. Are you about to say what a moving observer is like in the setup, or are you? I mean, if you're about to talk about that.
Yeah, I will.
Okay, good.
So the idea is that you actually, in order to coordinatize it, before you actually can speak about motion, you have to coordinatize each event. And in order to assign at least one coordinate, space coordinate, in addition to time, you have to have 2 observers or 2 observer chains, right? That's why I initially found at least 3 there. So now, if you take
okay, wait a minute. This is not obvious to me. Hold on a second. You're saying, in order to have a notion of space, you clearly are not going to have a very convincing notion of space. Well, I don't know. With a single observer, you've got. Are you saying that you're essentially triangulating position to find a notion of space, triangulating between 2 observers?
Yes, that's very close. Or in that mirror with the photon bouncing, you have to have at least 2 mirrors. You can't coordinatize it with a single one. You have to have at least 2 moving observers, or 2 observer chains in space-time, in order to coordinatize the photon bouncing between them. right?
Okay, so then can you you're about to describe? So you've got these. I mean, if I just think about points on the plane, and I look at the distance to, the point at x0, y0, x1, y1, and then for every point in the plane, you're saying if I know the distance to x0, y0, x1, y1, that's not enough. There's a ambiguity, right? But that's probably resolved by the direction of time. Is that correct? In the two-dimensional plane, Euclidean plane, knowing distances to 2 points is not enough. There's one ambiguity. You can be on either side, right? This making sense?
Well, if it's two-dimensional, two distances to 2 points, I think it's enough. It basically defines 3 points.
No, it's not enough. You can have a triangle that's pointing. Look, imagine you have 2 points on the x-axis, okay? And you know your distance to both points on the x-axis from a given point. You can either have the thing be an up triangle or a down triangle. There's just a single ambiguity.
Yeah. That's why I guess we only deal with the coordinatized, this influence idea. You have to only speak about future projections.
Exactly.
So if you have a particle moving around and you have 2 observers defined, you just see where this particle influences those 2 observer chains and where it projects in the future on those observer chains.
Right.
And by quantifying it this way, you can extract all the coordinate, like this 1 plus 1 coordinates.
This is why GPS, you need to be able to see 3 satellites, but 2 is enough if you make certain assumptions. But okay, yes, I understand.
If you want to have an additional spatial dimension, you have to have an additional observer chain. Maybe a pair. Basically, 1 pair of observer chains adds an additional possibility for an additional spatial dimension.
Okay. But so what happens in our case where we don't have an integer number of dimensions?
No, that idea comes from the hypergraph. Here, I'm just talking about the causal graph and order on top of it.
Okay, but anyway, so we've got. Okay, so you're saying we've got 2 observers, 2 world lines, and then that's enough to be able to set up. And given that we know the relative. Go ahead.
That's enough, to compute these pairs of numbers for each of the event around this pairs of observers. So here I just quantified every event on a chain, right? And then I use those by projecting every event around it on those pairs of observers and future projection. Took a future projection, and this is those 2 numbers for this. This is event number 2, and this is the 2 events or quantities on pairs of the observer chains. Basically.
Yep.
This is not coordinates yet. This is just projection. This 8 and 9 shows this number on an actual observer on the first and the second one.
Right.
So it's just a
pair
of projections.
8 is the intersection time, the first intersection time on chain one,
yeah.
And 9 is the first intersection time on chain 2.
Yeah, basically, yeah, correct.
Okay.
So now if you have this set of projections, you should take symmetric and antisymmetric different, symmetric and antisymmetric part of it. You basically have time and space, delta t and delta x.
Let me try to understand that. So you're saying, wait a minute, if I take these 2 coordinates, are you going to explain this?
Mm-hmm.
Right.
Yeah, well, I'm computing actually, yeah. So if you take these projections and just take a sum and a difference, sum would be Knut claims that it's going to be a delta t, so a time difference between, or not a delta t, it's going to be just a coordinate t, and this is going to be an x coordinate. So this is the way we actually coordinatize each event, just given 2 observer chains.
I'm a little confused. So the
Yeah, you
second
might have to
number,
explain that.
if you gave me the average, if that second number was not the sum, but was the average of the two times on the two observer chains, I would sort of understand that. Whereas basically what you're saying is an event happens, and if it's really close to chain, no, I'm actually confused here. This is saying that the delta, the difference of the arrival times of the light cones on the two chains, that difference of times is kind of a way of measuring position, which is not surprising. Right?
Yeah.
Whereas something like the average of the times is more like a notion of measuring time.
Yeah.
Right?
So the plus is the time here. So the second one is going to be time coordinate here.
Yeah, although it would be a slightly more natural time coordinate if you took the average rather than just the sum. Doesn't really matter in the end, but
Yeah,
it would
yeah.
be right.
Yeah,
So you,
I think even the Knut just divides it by 2, so maybe that's correct. But this time, at least, everything is integer.
yeah, I understand. But so you're saying, yes, okay, this makes sense. This is kind of an operational way to measure position by knowing how long it takes your light signal to get to each of your fiducial, marks, so to speak. Yeah,
Yeah.
makes sense.
Yeah. So, and here is basically all the events that are quantified nicely by those pairs, this pair of observers that I pick above. Both of the projections, future projections, can nicely project to those observers. So I can coordinatize this part. This is the actual layout that you get from it.
Okay, but the other events there are not coordinatizable that way because their future light cones intersect with future pieces of those observers that have not yet been generated. Is that right?
Yeah.
Yeah.
They just don't have any event on the observer chain in their
Because
future.
it's a finite observer
They
chain.
don't influence. Yeah, because it's finite. Or maybe they go in the completely different directions or something.
Yep.
So, and this is like already layout represents a Minkowski space. Like there's no line that with a higher than 45 degrees angle and so on. So you can already see from this picture that there's like all the structure of the caudal nature preserves. Yeah.
Wait a minute. That's the subgraph. What is that subgraph?
This subgraph is this red part.
Okay,
only
fine.
all those events that we were able to coordinate by those two observers.
So it has to be the case that it's in the past light cone of somewhere on that observer. Yeah, in fact, it could be on the past light cone of the final point of both observers, right? It's the intersection between the past light cones of the final points of both the observer world lines, is it not?
Well, yeah, somewhere there. I think I should have actually drawn the observers here to make it more apparent.
Yeah.
Okay.
I think this one and this one. Yeah, here actually what it shows. I think this. Okay. This is the observers, and this is all the particles that I can consider. And this is only the events that I can coordinate.
Yep.
And I think it's actually not visible here, but it is possible to have an event with the same coordinate because they can like go through each other and project to the same point on both of the observers. So it's actually impossible to distinguish some of the events given just this pair of observers. And it also can be seen when you actually compute all the velocities for pairs of this, for pairs of events. So if you like pick any pair of events, you can also assign a vector, right? And this is like an actual vector. Well, not a vector. I'm actually computing an angle because it's an arctan vector. So if you just for any pair of events, I compute an angle, and sometimes it's indeterminate because some of the projections project to the same point.
Wait a minute. Wait. The velocity, you're using your delta x, delta t. Your velocity is delta x over delta t. Is that correct?
Yeah.
Okay.
This was only the coordinates. In order to actually have a delta, I have to take pairs of them. So this is for all the possible pairs. I compute an angle by just dividing them and taking the rectangles to compute an angle.
Yes. Okay.
And this is like a quick FTL test. All the angles should like be smaller than 45 degrees.
Yep.
And there's nothing higher than that. All right.
So sad.
Hmm?
I mean, it's presumably it has to be that way for causal graphs.
Yeah.
Right.
Yeah.
The-
Well, for every partial order. Okay, this is just shows that which events actually have this property that indistinguishable for these pairs of observers. So all this subset that I highlighted have the same projection.
Sorry, what are you doing here?
I'm just showing that which events have the same projections. So they all project to the same event on green observer and to the same event on the blue observer.
Okay, so can you move the n around just so we see some other examples? Okay, so these are things whose future light cones, all of those events have future light cones that intersect in the same place to green and blue.
Yeah.
Okay. Okay.
What if you add more observers? Will the events like stop to being projected to the same point or not?
Oh yeah.
Yeah.
But if you wanna like embed it into 1+1, 2 observers is enough. It's a bit. I think this is just the artifact of discreteness here, right? Because we're sprinkling on a +1+1 dimensional space, so you have to be able to distinguish them. But from the point of view, just these pairs of observers, you can do it.
So basically, in the limit, when you look at the connections to everything else in the universe, there won't be such a situation that different events have the same coordinates.
So yeah, it's basically like looking at the same point. It's like if you look at to the sky, the single point star and some star behind it, also in the past of it, so that each like photon going through to us from the closest star and to the farthest star, but it kind of arrived at the same time. You can't distinguish those.
For photons.
Something like that.
For photons. Because they're light-like objects.
Yeah.
Which is the same thing the edges of our causal graph are also light-like. Right.
Well, from the point of view of observer, not always. It's like if you look here, not all of the edges actually, in the usual sense of a special relativity, not light-like, right? Because they have an actual velocity.
Yeah, fair enough.
It's not a speed of light.
In your definition of velocity, yes, I understand. Okay, this is nice. Let's see where this is going, and then we're going to probably need to come back to this.
All right, and here, well, this is like an idea of actually computing frequencies of those influences. Right now, if you take again the same observers and some particle, and then compute how many actual events intersecting an observer. So you can just count in a rate, and also just have pairs of events because you have 2 pairs of chains, 1 pair of chains. Right now you have 2. When you compute this pair of rates, you can using it actually compute the energy and the momentum with the same idea by taking its symmetric and symmetric part.
Well,
so it's dual to the space-time.
Yes. I mean, look, in our model with the identification of energy being flux of causal edges through space-like surfaces, I mean, are you assigning an energy to a single? I'm not quite sure I understand this. The energy, what's that energy being assigned to?
Well, it's observer dependent. It's assigned to a particle. Here, I have like generated three observers above, right? It's like where,
Uh-huh.
like for example here, right? I took two static observers and some random particle.
Yep.
So I'm assigning an energy to this particle by just
Yep.
counting how many like future projection events influence both of those observer chains.
Okay.
So I can compute a rate for the green observer and then compute a rate of influence for a blue observer, for green and blue, and also this rate, like R1 or R2. Right.
Okay.
And then there are like symmetric and anti-symmetric parts, like what are corresponding to energy and momentum and mass, like that, like a geometric mean.
Interesting. Okay.
And by construction, this kind of holds. It's not a perfect yet because this is how it's constructed.
I haven't seen this part yet. I don't think we got this far.
Yeah.
I'm not completely understanding this. Okay, so you're saying that first issue is relative to two observers, you can determine the position and local time of a given particle, right? That's one thing you can do, given these observers, by looking at where the light cone from that particle, from every point on that particle's trajectory intersects with, you can slice up that particle's trajectory in time moments based on the intersection of its light cone, of the light cone from those time moments with every successive piece of the sort of fiducial of the observer world lines. And now you're saying, in addition to doing this, I mean, I don't understand what the energy.
Well,
what's
think
the
of it as
relationship?
taking a dual. Just think of it as taking a dual because this is essentially a frequency. Like by projecting, by taking future projections on observer chains, you're computing intervals, like a length intervals or time intervals on this chain. But by computing frequencies, you're just taking a dual. So a natural dual of the like space and time is your energy and momentum, and you just do exactly the same thing by taking symmetric and antisymmetric part of rates in this case.
What is the dual? Describe what this dual operation is for the original causal graph, the particle world line on the causal graph versus the observer world lines on the causal graph. How do you compute this dual quantity?
I actually just by counting how many events here. For example, I take the, for example, this is one observer chain and this is another observer chain. Observer one here is an actual particle, right? So its future, which is the vertex out component, its future cone, and how it intersects with the first observer and the second observer, and how many events intersect there, scaled somehow, doesn't matter, right? So this, just by counting how many influences this observer particle has on observer chain, you just define your influence rate or frequency.
The difference is, one thing you're doing is you're saying the position is defined by the minimum value, the minimum, the first overlap of the light cone with this world line. Whereas here you're saying, look at all the volume inside the light cone, everything inside the light cone, and which is very similar, and which is essentially the difference between, you're looking at a single vector and you're looking at some transverse thing relative to that vector. And I think your division here is basically computing a flux of causal edges, because this is saying what causal edges, the vertex out component is a cone's worth of causal edges.
Yeah.
And this is saying which causal edges. So it's some kind of diamond type thing. There's a cone of causal, well, maybe not, because it's going all the way down that world line. So it's just Okay, but that division, that denominator is non-trivial because that denominator is telling you essentially is turning this thing into a flux, right? Whereas one case, all you're doing is you're computing what's the first point of intersection, whereas in this case, you're computing how many intersections are there divided by some normalization factor. Is that right?
Yeah. This is just a length of the chain.
Okay.
Just dividing by the length of the chain.
Okay, but in a very simplistic way, we could draw a picture where we're showing, a light cone coming from the particle, and it's what is its first point of intersection with the observer chains versus what is the complete flux of, what's the complete projected, content of all the causal edges which intersect that observer chain. I think it's exactly what you're doing. And I'm just trying to internalize the difference between just knowing the position and knowing, just knowing the time and knowing the energy. And the point is that what you're saying is the time is just this distance to first contact, and the energy is the total number of edges to get to that observer chain. Is that right?
Yeah, basically you have to it's the same problem as it's like signal processing. How you compute frequencies, you have to have some extent, and in discrete cases it's very tricky. Like when you can define coordinate by just this first contact point, but you have to have some extent in order to define frequency.
Yes, right. I don't think. I mean, well, okay, you can call it frequency. I mean, you can call it flux, right? Which is it's the total number of causal edges which get there, as opposed to the position of the first causal edge. I think it's very nice. It's a fine distinction. I mean, that's the distinction between time and energy, and we're saying, time is the number of computation steps it takes, and energy is all the ways that different computations can get you to this point, I think.
Yes, right. Look, it seems consistent with the original definition of energy given in the physics project book, except now it's actually observer theoretic. This is exactly what we're hoping for.
Right.
Yeah.
I mean, but let me just internalize that for a second. I mean, so what we're saying is energy is the total number of causal edges which get you to this point. So energy has
it's not really edges.
What's that?
Just not really counting edges. That's what
what are we counting?
That's what I'm looking. Well, we're counting events.
Yeah, but we're also counting events that intersect with this world line. So that's some kind of slice of, that's what I'm not quite getting. I mean, it's something very much like a flux, but I don't completely understand what that is doing. But okay, I more or less get it. Maybe we should keep going. Although I think there's more to understand right here. But yes.
So at this point, we kind of end the special relativity case. Now we just extend this.
Well, actually, Nick, you've spoken in the past about your hesitancy to treat energy in terms of flux of causal edges, and your preference to model it in terms of events. So why don't we play that out a little more? I know that you have more to say about it.
Well, for example, I've seen it even in the literature, in the causal set literature. They usually count not just like edges. Sometimes there's like counting of events plus some term counting edges plus some term counting triangles and so on, right? And that's how you define like curvature, for example, and then action. So I've seen even like math like that. So maybe it's depending how you want to extend it, it can be very complicated.
But Nick, what's your physical interpretation of a causal edge?
Physical is just a causal influence, right? It's just
Yeah.
cause and effect, right? So that's it. It's just order.
Right, but the interpretation that we've had is that energy is roughly the density of activity in the system. That is the rate of causal edge generation. Rate measured relative to something, and you've got to say what's measured relative to, which is what you've been getting more sophisticated about.
It's just weird to count actual edges, right? I understand it by counting events, but that's where the action is happening. Event is an actual
Yes. No,
application of a rule, for example.
well, but it's
Just for
events
example,
which are affecting the observer.
yeah, and it's weird because even events, those causal edges, they're not. You can add those depending on your transitivity, right? So it's kind of weird. Your causal graph is isomorphic, is transitive.
Yeah.
So you can add all those transitive edges in. It doesn't mean you add more energy in any way. So that's why it's weird.
Right. All right. Let's go on to your observer antichains.
Okay. So now we're gonna do some quantum mechanics. We're gonna try it. So this is not already. So now it's not just Knut idea. This is just my idea by extending this chain projection to anti-chain and trying to quantify it and extract quantum amplitude instead of coordinates.
Okay.
Right.
Okay.
So now you have to do multi-way graphs, not just a single-way causal graph. So now I think I only deal with the simple string substitution cases here, and I do the same kind of idea of tracking the im. This is like just showing where the single im manifests itself in the multi-way causal graph.
Okay.
So now it's not a longer single chain. Now it's like have multiple chains in different branches of future.
Yep.
Okay.
That's the idea.
What's this thing though?
Well, this is the branch graph, but it's not like branch graph in the what we usually deal with. Is the because this now has branch connections between events, but you basically constructed a similarly. Whenever you have a branch, you connect events together.
Which events?
But is this for one eam?
Produced by a branch.
How does this graph relate to the graph above? Maybe I should have just looked at the code.
This is not tracking any IMs. It just shows the causal structure with some branchal edges overlaid onto it. So whenever you have an actual overlapping instance of events, right, when they overlap and the branching is happening, you connect those events branchally. You indicate it like there's some kind of correlation happening. Right. Okay. So you don't connect space-like separated events. You only connect with the branchal edge those events that happen due to branching or overlapping.
Yeah.
So this is what just shows it.
All right. So something exciting that could be about to happen is some coordinatization of quantum amplitude space. Are you going to achieve that or not?
Well, not quite, but I have like some idea how to do it, but not exactly how. But I'm going to describe an approach.
Okay.
So here, for example, now I have like actual anti-chain observers. I'm tracking like 3 separate IMs here, right? Some random IMs that I decided to choose here, and just this is the actual subgraph.
Okay, but these are transversals. Basically, these branchial graphs that you've got these time-like edges that are branching time-like edges, like the 3-eam. The thing that started as a 3-eam was in general a multi-way, a subgraph of the multi-way graph.
Mm-hmm.
So it's a bundle that and then the and now you've got the branchial graph for that bundle That's like showing you the cross-section of the bundle. Is that correct? The cross-section of the subgraph of the whole multi-way graph.
At a particular time step. So here just pick a particular time step, takes the subgraph, and dropping out all the causal edges, so only the branchal edges for particular im on the particular time step. And this anti-chain, I call it anti-chain observer. So instead of having a chain tracking a particular im, now we have an anti-chain tracking a particular im. So I'm also modding out all the space. You can also think of it. Right? This happening in each branchal slice here, corresponding to each anti-chain observer, happening on a single location corresponding to that im. There's no space now. There's only a branch.
Right.
Branch time.
This is quantum mechanics, not quantum field theory. It's just a quantum mechanical setup where the only non-time extent is branchial space. There is no separate space here.
Yeah, well, maybe a little bit leaking here because all the events not just influence a single im, but also like outputting other ims, but it's not shown anywhere.
Yes.
You're just tracking a single one. Okay.
Yes.
So and now and this is like the same observers colored on top of the whole causal multi-way causal graph. This is the same branchial edges as above, but also covered by observer. Or maybe it's a causal edges covered.
Okay, but these observers are now multi-way observers, yes?
Yeah.
Yeah.
I guess you can also say that the fact that it's disconnected here, it can also mean that it doesn't have to be the same actual observer, because the way the setup works, you can create the same im on separate branches, right? You can track the same im through multiple branches, but it can also be created on multiple branches. So It doesn't have to be disconnected.
Okay.
So any connected component will have to be an actual observer.
But are these ems, when identical ems are created, you're saying, what is the equivalencing that gets done in the multi-way graph?
Well, I'm not doing any equivalency at all, because I'm not dealing with the multi-way graph. I'm just dealing with the multi-way causal graph without any equivalency at all.
I see.
Yeah, I only have a set of events in their causal relationships.
Right. Okay. All right. What happens next? Cliffhanger.
Well, now you can also take like a nice anti-chain and cover multiple observers on it, right? Take the same time step and take multiple observers. Now we have the same way I took multiple chains, the causal graph. Now I took multiple
several anti-chains. Yeah.
Corresponding to multiple observers. And now I can project to it also in the same way, like take a future cone and what is the intersection of this future cone with our anti-chain for all observers. And here it's like different events projecting on this anti-chain. So now we have like, let me stop somewhere. I know here. So this means that some event in the past of this anti-chain projected on the red observer here and on the green observer here. And here these actual observers actually share an event and so on. Yeah. And now the idea is you can also quantify it, somehow do quantum measure theory on top of it. So it's you clearly can do classical probability theory by just counting intersections of events. This is like an unfortunate clash of terms now, because in probability theory, event is like a set of outcomes, right? But here, event is actually a single outcome, so it's a little bit confusing. Now you have, when you project on an anti-chain multiple events, in probability theory you call this subset an event, right? So that's a little bit confusing. But now you have this subset of our elementary events given an event and probability, gives an event and probability theory, you can construct a probability theory on top of that, depending on what actually happened during
But I
the
mean,
measurement.
The
For multiple
point you're
observers.
making is that our events are much more granular. They're on-off events, whereas in probability theory, an event is something that has certain probabilities associated with it. So it's not an elementary event. It's an event made from an aggregate of lots of events with certain probabilities. Is that right?
Yeah, there's a whole event algebra. There's like atomic event, which is just a single outcome, and all the power sets for those, right? Also constitute an event. And you can just given an event algebra, you can construct a probability theory, just defining some measure on top of it. And
Yes.
what differs for the quantum case, your measure is a little bit different. And that's the problem. Where's the problem lies? How you actually define this new quantum measure when you just have a bunch of events interacting with each other by projecting those on the observer anti-chain.
Right.
And that's the thing I haven't quite figured out yet. How do you decide? How do you define this kind of quantity, like decoherence functional or quantum measure? So,
I'm not understanding this. Hold on a second. So let's see. You've got this slice, which is a branchial slice, effectively. And now you're asking here, for these light cones, which are actually entanglement cones, those entanglement cones intersect this branchial slice differently, and that's why they're different colors in different parts of this branchial slice. I mean, this branchial slice is a version of instantaneous space, except it happens to be branchial space. Just like we could construct from the causal graph a notion of instantaneous space by doing a branchial graph of the causal graph. That would give us an instantaneous notion of space, physical space. This gives us an instantaneous notion of branchial space. And a given, it's just like saying you release a bunch of test particles in physical space, and some of them will wind up in one region and one will wind up in other regions. So it's the same kind of thing in the multi-way graph of things landing up in different parts of branchial space, I think. But now, what is the...
Yeah.
Why do you call it decoherent?
One way of thinking about it is just when there's if you have like red anti-chain observer here, and not all of the events of it or that manifest this observer have the projection of your event that you're measuring. So you just have this particular event in the past that you're measuring, but it not manifest itself in all the branches of your observer. It just means there's not 100% probability to observe it.
Sure. Yeah, I think so. So in other words, you're saying that the way you are doing essentially the quantum measurement thing, and I mean this is where sort of there's a Born rule question that should come up here, is that you're saying given this observer who's being modeled by just this bundle in the multi-way graph, you're defining the observer is that bundle, and then there is some process that's taking place that the observer is trying to observe. And now the question is the events in the process. Does the observer, how does the observer project? How are the events in the process projected onto the edges which represent the observer? Because that's what's going to determine, in quantum mechanics, that's what's going to determine the bra versus the ket. This is the projection of a state onto a given basis state for the observer, if I'm not mistaken.
Yeah, something like that. Yeah.
Derive the Born rule. You're close. You should be able to figure out from here how to get to.
There are multiple ways of approaching it. Actually, Kevin Knut have also some ideas. He doesn't talk about anti-chain projection, but he kind of derives it in a similar manner how he derives the special relativity above, by just taking some some quantification of events, but now you also have a pair, but he associates the pair to a quantity and to an uncertainty. So if you had a way to quantify each event, not with a space and time coordinate, but instead with some quantity and its uncertainty, just a pair, you can make some arguments towards that. The only way you can like compose these events is the same way as you compose complex numbers, and all the like Feynman rules, Bond rules, all just pour out of it.
Wait a minute. Is this
Naturally.
you're saying? Is this a Jonathan argument? Is this something? Where did you say this came from?
It's the same guy as Kevin Knut with the projection theory about.
But also, isn't this something Jonathan has looked at as well? The
Well, Jonathan also derived the quantum mechanics from the branch-hole graph, but he kind of defined it differently by assigning a metric to each branch-hole edge, right? Which is 2D metric, and then just extending it to the Hilbert's projective space and taking a limit.
well, okay, but so I mean, what we really would like to do is a very careful derivation here of I mean, maybe we should invite this Kevin Knuth character to join us on one of these streams if you think.
Yeah, I've been considering reaching out to him. Wanted to see how much mileage Nick would get, but he's continuing to make use of his papers. So, we are looking
Looks
for
like
different
he's
academic
involved
partners.
in small world that it is. It looks like he's involved in this Galileo project thing as well.
Okay.
Oh, the small world.
Hey, I'm like almost 10 minutes late for another
Yeah,
meeting.
I'm
I wanted
late.
to give us a little bit of some extra time
Okay,
just because this
scroll
is
to the
interesting.
very end, Nick. Just to
Well,
just to see.
what else is there?
No, it's kind of the end. Then I have just a bunch of outtakes, yeah. Which is I don't know. This is like the idea when you have if you have an additional observer where you can do a Pythagorean decomposition and add an additional spatial dimension.
All right, let's just summarize what you're showing here. I mean,
What, the overall notebook,
yeah,
Stephen? Yeah.
yeah. I mean, so the first thing is you are finding, I mean, I know there have been attempts to axiomatize special relativity and to axiomatize concepts of world lines and things like this. What you're doing is essentially a nice, clean kind of, I mean, the concepts of special relativity, like a notion of time, a notion of position, and so on, you are saying how those can be measured by beam level observers, which is all you need for doing special relativity, I think. I don't know how you measure, and this would be another interesting challenge here, when you want to measure a gravitational field, you're going to need more than this. And in fact, you're trying to measure a gravitational field, that is a specific case where you're going to care about that bundle of observer pieces, the observer has a tidal force acting on it. The observer, internal to the observer, can feel the tidal force by the deformation of the bundle of time-like edges that represents the observer. So it seems to me that would be an interesting exercise to go beyond special relativity to say, how do you measure? Has Nick already done that?
I'm just
No, we haven't gone towards GR yet at all. No.
I think it's going to be a matter of computing this influence rate, but on a longer observers and also depending on the length of it, because here just took the whole observer, but if you computed running rate through an observer chain or through a particle.
Right. The other issue that we have is, you've got energy momentum here, and it will be very nice to be able to derive the relativistic transformations of energy momentum I mean, okay, wait a minute. You haven't really got a notion of frames. Like, you can't identify sort of commonly used frames, like an inertial boosted frame, for example. That would be another thing that's very useful to see here. I mean,
Well, well, Knut papers have it, basically how you can at least show the Lorentz transformation from this kind of projection. Like,
okay.
I haven't included it, but yeah, but when you define your projections and derive your coordinates and speed and velocity, you can also make case how the Lorentz transformation works, and it works.
Okay. Well, so I think you should very, very carefully go through and, it's like, imagine you're writing a relativity textbook, but using just this stuff.
Yeah, right.
What will be in it? Where's the boost? Let's look at the boost. Then, the big challenge will be an accelerated observer, for example. What does that look like here? I think an accelerated observer is, your observer chains don't have to be inertial, as you say. But the notion of inertiality, so to speak, depends on, for the same reason the gravitational field is arbitrary, until you've got, I suspect what you're basically saying is you can't know what the gravitational field is until you've got some extended number of observers in physical space. That a single observer can't know, a single point observer doesn't know what the gravitational field is I think your claim. So an accelerated
but
observer.
I think the pair of observer chains is enough to make some measurement.
Yes,
because it's already enough for energy and momentum.
Right, but so why don't we look carefully at, a boost? Okay, it's showing, and maybe it's obvious from what you have here, that the relativistic transformation of energy momentum is the same as the relativistic transformation of time-space. It's probably obvious from what you have here. I mean, that's something.
Yeah, it should be.
Right, I think so. And then there should be a boost. You should be able to just figure out, what class of foliations. Well, is it a class of foliations or is it a choice of observer? It's a choice of observer that is a boosted observer. And then all these things should flow through of that boosted observer should see energy momentum for things that are, transformed in the way that in the Lorentz transformation kind of way. I mean, that's one thing. And now in the quantum case, you're saying, this is where you've got branching brains in your quantum case, because you've got those world lines of observers that are no longer single world lines, but are branching world lines.
Yeah.
So now the question is, right? So you have a branching world line, and now the question is, when you project that branching world line onto a world line that you're trying to measure, that's where you should start seeing Born rule type stuff show up. And that will be a very nice minimal place. I think it will work. I think it has to be followed through carefully. But what you're basically saying is you've got a way to assign probabilities, and you've got this raw observer observing raw EAM level events, so to speak, or raw. And now the question is, how does that observer, what's the calculus of the probabilities observed by that observer? I think that's what.
The asymptotic. Yeah.
And you should
the actual branch structure takes into account.
You should be able to derive a bunch of all these Bell's inequality like things or something like that about the kinds of observations. The thing is, what's interesting about this is how little is going into it. You don't have to have a model of particles. You don't have to have a model you don't even have to have a model of extended observers. You have an EAM level observer who necessarily is multi-way. And then the question is, how does a multi-way EAM level observer, how does that thing measure an EAM level process, so to speak? And the claim would be, even at that level, you might see the Born rule. I bet you will.
Yeah.
And you don't need to go to any kind of more elaborate. So in other words, it's an multi-way EAM observers watching multi-way EAM processes. Necessarily, that projection involves something like this complex number story.
I mean, as I was saying, I think yesterday, it's much better if this meta modeling framework begins with a nice way to computationally extract energy values before we get to particles. Because if it was the other way around, we would really be in trouble. However, I still have misgivings of this notion of EAMs actually making observations. I mean, it's helpful for the whole world line model, but
Look, I mean we
unless,
and old Albert are in the boat together, because the fact is he has world lines making observations, and when it comes to general relativity,
what does observation really mean? And it's not in the in EAM does not have a computational sophistication to actually make an observation. So I think this notion of an observer is still somewhat nebulously defined.
Yes, but the problem is, look, an observer ultimately is an observer that we care about, and is an observer which is going to transduce the complexity of the world onto something that fits in our minds, and for which our minds can be fairly certain that a definite thing happened. Right? In other words, it's no good to say, oh, it's all still multi-way. Well, our minds don't go multi-way. Our minds have, collapsed the wave packet, so to speak, to something definite. And so what I would expect to happen is, this is the question: how far can you go without actually having? This is related to the following question. So, with respect to making measurements in a gas of pressure, to what extent do you need the notion of a solid to define the notion of pressure in a gas?
Right. Yes. Yeah.
Right. And so it could be, and in fact, because I've been studying the history of kinetic theory the last few days, I can tell you that, for example, things about the viscosity of gases were used to make which do not require. You can effectively measure things about molecules and gases from viscosity without having any notion of a solid boundary. And so the question is here, to what extent, because a solid is something where there are many degrees of freedom that are all being made to act in concert, so to speak, which is what you think of as being a more credible observer. But the issue is, right? So it could very well be that we can, and I think this is kind of the story of the project in general, is that physics is actually simpler than you think. In other words, you don't need to have these very built-up towers of stuff to get a lot of core facts about physics. And I think that's the question of can we nice and cleanly get all these things like the Born rule without going to, does the Born rule, what aspect an observer like us is needed before you get things like the Born rule? And it may be, and I suspect it is, incredibly little.
Well, we were debating this last night. I still reserve the suspicion that some of these things won't arise until you get to a higher scale, but we'll see.
I also have an additional concern that it's not like this kind of models not necessarily give rise to a quantum theory, but like a generalized quantum theory that people can work on. It's like even with this quantum measure theory, there is the whole hierarchy of this kind of rules that you can construct. And it's not obvious that you only stop on the first one.
Right, but I'm telling you, it's going to be like solids and gases. That is, you can have a great theory of gases, but, and it's sort of like a theory of solids, but you have to take a bunch of other limits to get to the idea of solids. And by the time you're going to make a measurement of pressure, for example, you kind of need solids. And in our case, the question is, in the case of molecular dynamics, I don't yet even know what the minimal model of a solid is, because I don't even know when you hit the wall of a container and you dissipate the detailed degrees of freedom of all the molecules hitting it. I don't even know how that works, really. Because that's what you ultimately got to do. You've got to take a large number of degrees of freedom and somehow conflate them into a smaller number of degrees of freedom through some process which is fast compared to the process that is operating on the small number of degrees of freedom. And, yes, there is a scale separation there, just like there is a difference between the frequency of interaction between molecules in a gas and the frequency of interaction between molecules in a solid. And that scale difference there may be a bunch of phenomena that are not visible without having that scale difference.
Yeah. Right. Guys, I'm almost half an hour late to a meeting, and
it's
really not my style. I don't like
and I need to go too. So this is good. Thanks.
This was fun. Thanks, Stephen, for joining.
Thanks,
These were some good comments.
All right. I look forward to seeing more. Okay. See you guys soon.
All right, cool. Cheers, guys.
Okay.
See you
Bye.
soon.
Bye, everyone.